Hello everyone, welcome to our AI tutorial on learning with small data. This is Jessie from Penn State, and this is a joint tutorial with my student Huaxiu and also with Professor Fei Wang from Cornell University. So the motivation for us to give this tutorial is because nowadays everybody is talking about big data error. For example, we all know ImageNet has a huge amount of labeled image data. As of July 2020, it has 14 million images. However, we often have the problem when we try to address other problems, not about image or maybe natural language processing. When we address the real world problems, we often realize we only have a very small amount of data, which is the reality in today's big data era. Take this for example. If we talk about image classification, even though we have a lot of images, when we talk about a specific classification task, say we want to classify an image, whether this is a Boston Terrier or French Bulldog, well, they look very similar. These two breeds look very similar. And if I give you a new image, maybe if you're not an owner of a Boston Terrier or French Bulldog, it's going to be very difficult for you to predict what is the label of this image on the right. And actually, this is also a Boston Terrier. So this is just an example when you only have very few training samples for a new task. The learning, we want to talk about how to learn from the small training data. And this is another example. Say you want to teach the robot to complete some task. And this is example says the robot can learn to place the peach into the red bowl after watching the humans to do so. So maybe the humans will make some examples how to place the peach into the red bowl, and the robot will repeat. And maybe next round, the human will take some other actions, and the robot should learn quickly from the new task. And this is also a real problem, say, in the smart city applications. Say nowadays, we have a lot of open city data portals. For example, we have NYC, Chicago, or Boston. But those data portals do not necessarily have the same amount of big data. If you search for taxi data on those platforms, we may have very nice New York City taxi data, very complete data. We also have quite reasonable amount of Chicago taxi data. But if you search for a taxi on Boston platform, there actually is no such taxi data. So say if you want to predict the demand, the taxi demand of a city, what to do in Boston when you don't have any of the data, or maybe you only have very little taxi data. So in terms of the methodology, if you only have small training data, there's two ways you can think about how to mitigate the issues of small training data. You can either borrow from auxiliary task, which means there may be other machine learning tasks that you can borrow from. And those tasks usually have more data that can train a more robust model. On the other hand, you can also try to borrow knowledge from experts. So this is the second category where you can get help from domain knowledge. So our tutorial, the methodology part will be two parts. We'll talk about how to learn from auxiliary task, so that can help with your target task with only small amount of data. Another category is how to learn the knowledge from domain expert and how to transfer that knowledge into your target task. And then we also will talk about two applications, one application in healthcare and another application in smart city, to give you a more detailed explanation how those methods are used in the real world applications. So I will go ahead and get started with the methodology. So in general, we will have those terminology. So in terms of the auxiliary task, we usually call them the source task. And those source tasks usually have reasonable amount of data to train a reliable model. And then the target task is the task we care about. And usually that task only has small amount of data. So transfer learning basically is you learn a model from the source task, and then you transfer the knowledge from the source task to the target task, where we learn a new model. So there are three categories of under the big umbrella of learning from auxiliary task. One is transfer learning, where usually people are talking about there's only one task in the source domain, and there's also only one task in the target domain. And in the multitask learning setting, there are usually n tasks in the source domain, and there are also the same n tasks in the target domain. So these tasks are the same tasks. And then for the meta learning, so usually the source task has n tasks, and then the target domain has another task. So basically these three types of auxiliary task learning has different types of setting depending on the source task and the target task. Okay, so we'll start with the first transfer learning. Well, in the source domain, there's only one task, and in the target domain, there's also only one task, but a different task. And under the transfer learning, there are two types of transfer learning. One is supervised learning, and another one is unsupervised transfer learning. As you can tell from the name, so the supervised transfer learning is probably the most common type of transfer learning we often see, where the target domain has a few label data. Another setting is called unsupervised transfer learning, where the target domain, we have no label data at all. And we also call this domain adaptation. So we'll go ahead with the first one, which maybe many of you are already quite familiar with the method. Say now we are looking at the same target task we talk about. So we want to classify Boston Terrier and French Bulldog, these two breeds, which look very similar. And this is our target task. Maybe we only have 3 or 6 training data samples. So what you're going to do, which is very common practice nowadays, is you actually first train a model from the source task. Say you actually train a source model from all the ImageNet, from 14 million images. And then based on this model, you further build your target model. And in terms of the implementation, usually nowadays we all use neural nets for image classification. So we usually, for the target task, we have some shared layer, or you can call this tied layer. So basically those layers will be exactly the same for our target task. And then usually we have a few adaptation layers. And in this case, usually the tied layers are quite deep, but adaptation layers are quite thin. So you don't have that many adaptation layers. So basically you can fine tune this target task based on the tied layers. And the intuition is those lower layers usually capture the basic information of the images. And then the higher the layer, the more specific the problem is. As you can see, the layer 1, probably you won't be able to tell exactly what does it mean. this is the image, this is a face recognition task. And then layer 2, you start seeing the eyes, nose, mouth, those kind of features of the human face. And then layer 3 will become more problem specific, where you can actually towards more telling which face is this person, right? So similarly, the last few layers will be more specific to classify French Bulldog and Boston Terrier. Okay, so that becomes quite a common practice, the way we don't want to spend too much time on. And recently, there are also people working on unsupervised transfer learning, which means in the target domain, there's no label data at all. So a typical practice is actually we will define a distance with the source domain. So we add a regularizer here, defining the distance between the source domain and target domain. And again, since the target domain, we don't have any label data. So the way we define it will be defining on the feature space. So we basically want the features to look similar from the target domain to source domain. And typically, when we say the features look similar, we are not talking about original feature space, and we usually are talking about the feature space after the embedding using the neural nets. So we'll look at, so similarly, it will be tied layers and adaptation layers, and the tied layers is making these features look similar. Okay, so a very commonly used method is called MMD, maximum mean discrepancy, to define the distance between the source domain and the target domain. So basically, you can define a distance matrix between the features of the source domain and the features of the target domain. And in this case, we are using the maximum mean discrepancy. And this is a sort of first paper on this domain adaptation, which works pretty well, published in ICML 2015. And as I just mentioned, so the idea is that we have some tied layers, and in the adaptation layer, instead of doing the fine tuning, here we're doing a distance matrix. So basically we are adding a regularization to make the adaptation layer also look similar. So basically, those tied layers will look exactly the same, while the adaptation layer will look somewhat similar, but not exactly the same. And the distance matrix here, again, is using MMD. So after this work, there are many variations to define the distance between the source domain and the target domain in the adaptation layer. Another example we can see is instead of defining the MMD, they're defining the distance between the source domain and target domain as the norm of the feature space. So as you can see, the H function here means the original feature space X. So after transformation of G, where is the first few layers, and then after transformation from the F, which is the adaptation layer. So you can think about this is the embedding of the original feature space. Then we take a norm of that embedding space from the original feature. So basically we want the norm of the source domain and the target domain to be similar. So instead of using MMD, so here is using the norm of the source domain and target domain after the original feature or after getting the embedding of the original features. And also you can use adversarial to make the source domain and the target domain to be similar. So basically you can add a discriminator to discriminate these two feature space. So the idea is also similar. So to make the feature space of source domain and target domain to be similar. So that is about transfer learning. So next we'll talk about multitask learning. So multitask learning, when we talk about big picture, that means there are multiple tasks, both in the source domain and the target domain, and usually they are the same task. So basically it's the end task, how can they help each other in learning the model. And there's three types of multitask learning methods. The hard parameter sharing, soft parameter sharing, and task learning routing. So as you can easily tell from the name, hard parameter sharing and soft parameter sharing means the hard parameter sharing means the task A, B, C, so the multiple tasks, they will share some layers and they basically use exactly the same layers and they have their own adaptation layer. However, the soft parameter sharing means you are going to make those layers look similar by adding some regularization, but they won't be exactly the same. So they're more soft from that perspective. And then more recently, people start looking at layer routing. The idea of layer routing is, as we just said, this is the hard parameter sharing, where they share exactly the same layers of different tasks. And soft parameter sharing means they will make them look similar, adding some regularization, regularizations here. And then the layer routing means there will be some of the layers, they will make them exactly the same. Some of the layers, they will make them task specific. As you can see, the orange one will be the ones that exact the same. And there's some yellow one or green or pink one where they're task specific. And then there's some layer that will be shared again. So it's a very flexible design of the layers. We call this layer routing. And when you do say you want to do task one, this pink one, so maybe you're going to use those shared layer and the task specific layer, and then again the shared layer, and then the last one is the adaptation layer. So this is a very flexible design of the layer sharing. And that is a very recent multitasking learning, and there's some follow-up work on this one. So I will stop here, and then next, Huaxiu will take over to talk about the meta-learning part.
Thanks, Tracy, for introducing and discussing some methods to learn the knowledge from auxiliary tasks. Here, I'd like to discuss more about the meta-learning, which could be the key components of the tutorial. I will first discuss both gradient-based and metric-based methods in the meta-learning algorithms, which could be regarded as the two most popular algorithms in currently. I will also discuss some challenges in the meta-learning, like the meta-heterogeneity and like the meta-overfitting. Finally, I will discuss some preliminary works about the online meta-learning. Okay, let's start by just discussing the meta-learning algorithms. Here, before we start, we want to introduce what could be like the meta-learning. In the meta-learning part, we will also have some meta-training tasks, which could be like here we have different sports tasks, and we want to transfer this knowledge to learn a new task quickly. So meta-learning could be one type of the knowledge of the learning to learn. In this part, we will learn some skills, or like we will know how to learn from the meta-training tasks, and then we could reuse this learned knowledge to facilitate the learning process of the newly unseen tasks. Here we provide one specific example. In this specific example, we will discuss some few-shot image classification. During the meta-training process, here we show two types of tasks. Both tasks are few-shot image classification, which consists of two classes, and for each class it has 4 images. And maybe we have a lot of these tasks, like a training data set. Like first one to classify cat and birds, the second one to classify flower and bike. And then after that, we will learn some knowledge from them, and we will transfer this knowledge, this prior knowledge, to the meta-testing tasks. In this meta-testing task, we will use knowledge to classify 2 different unseen classes, so the dogs and otters. And we want only maybe each class only have a few data samples, and we would want to make it to generalize knowledge to the meta-testing tasks. Thus, we could regard the meta-learning as like for example, like compared with the supervised learning. Like in the supervised learning, we will have the inputs, and also with the output labels. And we will find our mapping function f theta xt to link the inputs and the outputs. And in the meta-supervised learning, besides the inputs for the current task, and we will also have a lot of meta-training tasks like we showed before. So we have a lot of scene classes and have the meta-training tasks. And we would like also output to the YT. And here we will see that the meta-training tasks could help us to find the link from the F, which consists of XT and other the knowledge from the meta-training tasks and to benefit YT. Okay, let's move to the first part of the gradient-based meta-learning. In the gradient-based meta-learning, we will model the meta-model as the transferable knowledge. So this transferable knowledge could be regarded as the model parameter initializations. So in the parameter, for example, in all the parameters from some neural nets. And also in the we also define the task adapted parameters for each task I as the phi I. And then in the training set, we saw some also called like a support set, and also in the testing set, we define as DIS and DIQ for each task I. And in the meta-training process for the gradient meta-learning is what we could regard it as a B-level optimization problem. In these B-level optimization problems, we have two levels of optimization. In the inner loop, we will find one algorithms and with support set to adapt the model initialization to its task adapted parameter phi I. And then we will use the task adapted parameters phi I combined with the query set, the DIQ, and with its loss function, and to evaluate the performance on the query set and use it to go back to optimize the parameter theta. Thus, we could see that in the gradient-based meta-learning, we would want to find a very good model initializations which could be generalized to different tasks. One typical definition of the gradient-based meta-learning is the model agnostic meta-learning. So in this part, we could see in this figure, so it's also illustrated how to use it for the gradient-based meta-learning. So in the inner loop, we will use the gradients to get its best parameters of each task. Here we see that the theta I1 star, theta 2 star, and theta 3 star. And during this time, so we will have the meta-training part. So the inner loop would be the gradient descent, and the outer loop will also to use it to optimize the parameter theta. During the meta-testing part, we will have the parameter theta minus also fine-tune the parameter theta to the using the training tasks. So we could see that in this model agnostic meta-learning, it optimizes a global pair for the different tasks, which can be quickly adapted to the best parameters. However, in the gradient-based meta-learning, we need to calculate the second-order gradient. So, but calculating the second-order gradient process is time-consuming. So we would like to optimize it. How to optimize it? There are several methods to optimize it. For example, like a full memo. In the full memo, so people want to optimize it by just using a first-order approximation for each task. And we could see we will like simplify the outer loop gradient as like we will evaluate the phi i's performance on the query set and go back to optimize it. Also, we will also get some other optimization first order approximation ways like the reptile, so which calculates the distance from the parameter theta and the phi I, and then go back to optimize the parameter theta 0. So in this part, these several methods want to optimize like the second order gradient calculation, and by using some like first order approximations. Besides this, there are also some works to want to optimize the gradient-based meta-learning by just considering the optimization trees. So to consider it, so mostly they will introduce the gradient preconditioning methods. So let's see here we have the normal gradient descent, so which is could be like the black line. So which we can see maybe it takes a long way to get the optimal value. But if we use a preconditioning methods, we precondition it, and then it can be like using maybe an optimal gradient, optimal optimization path. Thus, we want to like control the gradient descent by meta-learning and parameterized metrics that preconditioning the gradients. Here we can see in the right figure. So in traditionally, we will like starting from the theta to the theta prime, but we want to use some gradient preconditioning to move it to a second space, a new space, and which will be moved to the gamma prime. So this could be a strategy. Could be the preconditioning metric to do that. Here are several ways to do the gradient preconditioning. The first way could be like memo. So most of them are optimized the inner loop optimization algorithms. So memo is just for the gradient gradient descent. And in MetaSGD, so people use like a diagonal matrix, which could also be like they want to learn a better learning rate for each parameter, and then to optimize it. Later, like in the TNet, people will introduce another parameters omega to do that. So this omega could be involved for after each layers, maybe each convolution layers. So they will involve one times one convolution layers, which could be like do a linear mapping on it. And also like people do some meta curvature. So we use the meta curvature, which is defined by a function b, which considers both theta and the precondition the parameter omega to do that. And this meta curvature also could be a more extended version of MetaSGD. And the last one would be like the web gradient. In the web gradient, so people would consider the nonlinearity information which of the omega compared with the TNet. Then I will try to detail some web gradient. And we could see like we have the input x, and for each layer, so this is h1, and then we have the preconditioning parameter omega1, and then the h2 and omega2. And then we would get this output. And if we do the gradient descent, and we will find the preconditioned metric, the p of it. So this could be like the h would be updated by each task. So it responds to the theta 1 to theta 2, and this parameter theta. And the parameter phi would be fixed during the learning process. So it would be a globally shared parameters. So it seems like we found a metric p to do that. Okay, so this is what I want to cover in this tutorial about the gradient-based meta-learning. Let's now move to the metric-based meta-learning. In the metric-based meta-learning, we will have a support set ds and some query data samples xq. So in this part, we want to like compare each testing data samples with training data sample. For example, now we can see in this illustration, we have like 5 classes. For each class, we only have 1 image within each class in the support set. And then in the query set, and we will use the line to compare with this dog and this line. So if we can compare with this the query line to the support line, so maybe we can correctly classify the query data sample. And there are 2 issues in the metric-based meta-learning. So the first one is how to define the comparing space. And the second one could be how to define the distance metric, because we just want to compare with from the query to the support set. And here we will show 2 examples. The first one could be the metric network. In the metric network, we will use a mapping function to map each samples to the vector, and then use the queries through another mapping function to a vector, and in this vector level, we will compare with the distance about that. So in the meta training process, we will learn the mapping function phi theta, g theta, and f theta. And in the meta testing part, we will forward it to the network. We just forward the network. So we just need to compare with it. So this comparison could be similarity times the labels of each support samples. Thus, the symmetric-based meta-learning also will be called the non-parametric meta-learning because it consists of the parametric learner with the non-parametric meta-learner. So it could be in the non-parametric ways, so we just compare the query samples with some support samples. Okay, so another example could be people will extend the metric network to the prototypical network. In this prototypical network, we will also learn this mapping function f theta. And after learning this map f theta, f5, how to do the comparison. So in this way, we will try to construct some prototypes of each class, because for each class we have several samples, and we just want to get the prototype of each class. And here we see the C1, C2, C3 would be the combination of the samples belong to C1, C2, and C3. After that, we will also use some non-parametric matching functions with the various distance t to do the comparison of each. And finally, we can know what's the query sample x could be know the class of each of the query sample x. There are still more complex relations and distance measures in the metric-based meta-learning. For example, the first one could be like a type net. In this type net, we will have the feature extractor, and we will map it in the embedding space. And then it will define another space, could be like the task adaptive projection space, and do the comparison in this space. So we could all regard the type net, say, revise how to define the mapping function mapping space for comparison. Another way could be using the graph neural networks to do the comparison. So here we regard this problem as a future learning problem, as a semi-supervised learning problems. So we have a lot of nodes, and for each node, maybe one or several nodes could be like unlabeled nodes with the query nodes and with all the support nodes. And then we will through their representation, we will define its construct the graphs by defining its link. And then we will use graph convolution network to do the message passing. And then later we will do it several times to iteratively construct the graph and then do the message passing on each. And finally, we could get, we will do the inference by just in the query samples. So also I will mention to some relation network. In this relation network, so it's very similar to the metric network. So it will be mapping all the things to the feature mapping. And in the feature maps, so they will do the concatenation with for the queries, they will concatenate with each support samples. And through another layer, so it will learn the interactions between queries and the support samples. The last thing I want to mention is meta-optinet. In the meta-optimization net, so after we map it to the training samples in the embedding space, and we will define some weighted linear classifier to classify it. For example, like the SVM to do that. So this is several methods for the more complex relations or distance measures. Here we just mentioned two types of methods in the meta-learning algorithms. The first one is gradient-based methods, and the second one is metric-based methods. Okay, let's move to the second part. Is about some challenges in the meta-learning. In terms of these challenges, we will majorly mention the task heterogeneity and meta-overfitting. The first problem could be the task heterogeneity. we are now thinking, so previously, like the gradient-based meta learning, so they learn a globally shared model. And our question is, so is the global shared model enough for adaptation? So for example, the global shared model could be one model generated from the global shared parameter theta and to adapt it to each tasks. However, like our human beings, we may have some versatile tasks. For example, we can see here we learn some like linguistic courses, like syntax and morphology, and also like some physics tasks like mechanics and electricity and different courses, and also have some math courses like number theory and calculus. And we will have a new courses, maybe a group theory. So in these graphs, if we want to learn the new courses like group theory, so our question is, are all historical tasks useful to learn the new course? So obviously, we can see that the math courses may be very relevant to the group theory, and also some physics courses may also be relevant to this group theory. But we know like the linguistics do not pay any contribution on learning of the group theory. Thus, we will introduce some methods to tackle this tackle this challenge. As the first one, we will want to introduce the clustering structure to do the clusterings. So here, in this part, we will cluster like different tasks, maybe task 1, task 2, task 3, and task 4. In this part, we could see like the task 1 and task 3 belong to the theta 1, and task 2 belong to theta 2, and task 4 belong to the new theta 3. In this part, the model is proposed for as a hierarchical structure meta-learning process. So the key contribution is to want to balance between the generation and the customization. So it will organize the tasks by hierarchical clustering, and will also adapt the global initialization to each cluster of tasks. Here we could see like we have the task representation learning, and in this task representation learning, we will learn the representation of each task, which will be interacted with the hierarchical task clustering, and then to adapt it to the global shared parameters. I will detail the models step by step. So the first step is to learn the task representation. So the goal of the learning task representation is to like represent each task. So as our humans, we will first want to know what the task is. So in these models, they would like formulate each task to a differentiate representation vector. The solutions could be like the sample aggregation. So after we map each task to a mapping function, then map the sample representations, and then it would be aggregate to the task representation. Here, the aggregator is designed by an autoencoder structure. In this autoencode structure, it consists of one encoder and one decoder. So here, we use the recurrent structure as both encoder and decoder as an example. We could also tranche the encoder and decoder to different types of structures, like phonic layers. Here, in the recurrent neural network, so in the encoder, it will be each samples would be input to the encoder, and then we can get its hidden representations. After getting the hidden representations, the mean polling will be applied on these hidden representations. The reconstruction error is also introduced to improve the learning training stability. If we train from scratch and we did not know any information, so maybe if we do not introduce the training stability, so maybe it will be like the training steps would be it will be harm for the training process. After getting the task representation, the next step is to model the cross-task structure by using a hierarchical clustering structure. Here we can see that like we will like try to organize different tasks. Like for example, like our humans here, we show another example is like we have different logic tasks. like different sports tasks and different language tasks. And if we want to benefit as a new task, we want to locate it to most similar tasks. Maybe here is the sports task. And in this part, we can see the T1, T3 belong to the theta 01, T2, T4 belong to theta 04, and T5 belong to theta 03. After we getting the task representation HI, we would use it to query the clustering centers and try to find a path between the clustering structure. Here we have the task representation HI, which represents each task. So these clustering centers would be learned through the learning process and which summarize the historical information within the clustering centers. So after interacting with the task representation and with the different clustering centers, we could see maybe here in the first layer, so the green one would be most similar, and we will link to the green one. And the second layer, we will also link to the first part. And finally, it will be enhanced representations. So the clustering centers would be totally learned from scratch during the meta-training process, and will be save a lot of historical knowledge, can organize historical knowledge in the meta-training process. Majorly, it has two steps. The first one is the assignment step, which would be we want to assign a task to the nearest cluster. And the second step could be the update step, which is used to update the representation of a cluster. So after that, we could get the enhanced representation. The last step is to do the knowledge adaptation, because we have connected the structures from the model, and we will use the structured representations to customize the prayer. A quick illustration could be if we use memo and we learn a global prayer like theta 0, and which can be adapted to different parameters theta 1 star, theta 2 star, and theta I star. But if we want to customize it, so we will go one step beyond. So we will starting from the theta 0 and to theta 01, theta 02, and theta 0I, and to get the theta I star, theta 2 star, and then to get theta I star. And different modulation functions could be used in this training process to go one step beyond it. Here we show one types of ways to define a task representation informed parameter gate, which would be consider the enhanced representations and task representations, and using the getting functions to get the parameters OI, the gate OI, and which is be applied to modulate the initialization and get the theta 0I. Or this optimization process would be in the inner loop, the model would be starting from the theta 0I and then optimize to the theta I star, and then go back to optimize the model. In this analysis, we want to initialize of these models based on some basic analysis, which we also infer the generation ability of this part. And in this part, we think that the customized prayer could be a combination of a linear combination of the theta 0. And for the memo, if we learn a global shared model, so the BK could be divided equal to the I divided K. And there may be access to some BKs, which could be find a tighter bound if we have some customized parameters. In this part, so we will show one simple ways to prove it. So just go one green step beyond theta 0 and to get the theta 0 hat, and which could be represented as one type of BK. So we also want to show some interesting results on it. So by just doing the image classification, in this image classification part, which will consider of 4 data sets for fine-grained image classification. The first one would be bird, texture, aircraft, and fungi. So in this part, we would for each task, we would randomly sample one subdata set. And to construct a specific 5-way one-shot task, we will also randomly sample 5 classes and one sample for each class from the selected subdata sets. We illustrate the results on the 5-way classification compilation, and this can see like the models could be performance better compared with the previous models. And also we want to involve some continuing information on it. For example, like put the airplane in, and later and the first step select the data sets from two sub data sets, and later we will involve different data sets into it. And besides this, we will also like show some cluster assignment interpretation. So for example, like here we see plot the assignment properties, like a bird is very activated C2, texture activated C4, and airplane activated C1, and fungi activated C3, and the bird and the airplane also maybe similar activated C1 because they have some similar shapes. And the hierarchical structure also be plotted. For example, like a bird activated the second, the first node of the second layer, and the fungi also activated the first node of the second layer. So maybe they have some similarities in the environment. In this part, let's recap the models from the models, and we see that these models consider a hierarchical clustering structures to model the complex structures between tasks. However, it relies on the carefully handcrafted design, which we need to design the number of layers, the number of nodes in each layer, and how to connect it between the different layers. And it also limits the structure representation power, which only considers the hierarchical structure, and the node relations are used across clusters. So the questions could be, is there any way to find a more flexible and automated way for the structure exploration? Let's think about this problem. So we would have like a different clustering structure. Here is linguistics, physics, and math. So through this clustering structure, it would be moved to the meta-knowledge graphs. So previously, we used clustering structures to do it, but if we want to maybe like a more flexible structuring, knowledge structuring ways, so the graph structure would be a better choice. So another model could be like the automated relational meta-learning models, which want to automatically learn the structuring relations by structuring the samples as the prototypical based graphs, and then it will use the prototypical based graph to query the meta-knowledge graph for the historical information. So I will detail these models in the next slides. And the first step could be like, it will be used to do the task organized representation. So here we see that we want to like summarize different samples to its prototype. Maybe the different samples are from the green samples, the blue samples, and the yellow samples would be calculated its mean value between L of the mapping space and to get the prototype. And then it will be used to construct the prototype-based relational graph. So this prototype-based relational graph could be think as like the structure within tasks. So it will be models within task relations. Okay, so in this part, I've said so we will have some meta-knowledge propagations, which will consider as a prototype-based relational graph with a meta-knowledge graph. And this meta-knowledge graph could be learned from scratch in this model and learned and updated during the meta-training process. So finally, all these nodes in both two graphs are used to connect them and construct a supergraph. And after constructing the supergraph, and the information could be propagated from the meta-knowledge graphs and to the prototype-based relational graph, and which could be enhanced the performance, the representation of the prototype-based relational graph, which is related to the information of each task. After that, we will aggregate all the informations like from the original prototype relational graph, and also aggregate the information from the prototype-based relational structure. And later, this information would be adapted to moderate the models. Okay, so this is we want to like cover in this part about task heterogeneity. So there are for more task-specific meta-learning models, we can see like some models use the task conditioning and to customize model parameters or customize, like for example, the learning rate to make them as task adapted. And another idea could be like we should consider like Bayes models, Bayes perspectives in this part, and consider the deliberate process mixture and to model for the heterogeneous distributions. Okay, let's now focus on the part 2. In the part 2, we will discuss about the trend 2 is about the overfitting meta-learning. So in the meta-learning process, especially like the gradient-based meta-learning, we could see like we have like model initialization theta 0 and with the support set and DS, which will get the task-specific parameter 5, and then we can get like using the query set to go back to fine-tune to optimize the model initialization theta 0. And here we will have 2 types of generations in meta-learning process. We can see like the first type of generation is we call it like the task generation or like inner generation. In this part, we will have, for example, like here we want to like generalize, we want to adapt the model parameter initialization theta 0 to like maybe 5i or 5i. Here we would like to see that if we were using the support set, but the support set usually have only a few data samples, and then we get the parameters of phi, and usually it will involve some overfittings, and we'll have the task initialization generation. And the another part would be like the meta generation. In the meta generation, so we would like to see that the model parameters would be easy to overfit on all the meta training tasks. So after overfitting on the meta training tasks, it would harm the generation on the meta testing performance. Thus, there are 2 types of the generations of the meta generation and the traditional generation. So this overfitting in meta learning will affect both task generation and meta generation. Okay, let's see how to like overcome the task overfitting. The straightforward way of overcome the task overfitting is reduce the number of parameters, because if we have several neural networks and for each parameter we need to update it during the inner loop. So we will do several gradient steps, but maybe we will overfit. Thus, if we can reduce the number of parameters, maybe it can both improve the efficiency of the meta learning process, but also we can like reduce the effect of overfitting. Here we would involve the first work is called the caviar, which is in ICM 19. So in this work, the people will fix the parameters from the across different hidden representations. For example, here is HI, HL, and HL plus 1, and it's corresponding like parameters theta L would be like fixed during the training process. And how to achieve like the task objective values. Here they involve some like neurals of like phi, which could be like contextual information, and using this contextual information, the parameters from the contextual information to the next hidden representations would be could be fine-tuned or like during the inner loop. So compared with the original work, so here is the whole theta would be updated during the inner loop. So here we only have a few parameters to be updated. Thus, it can reduce the number of parameters and improve the generation ability, so improve the task generation. And a similar work could also be like the annual. In this annual, so they will like fix the rest of layer parameters. So maybe here, like if we have 3 layers, and the first layer and the second layer would be fixed during the inner loop. And in the inner loop only will be like update the head layer, so the last layer. Here we can see that it can also significantly reduce the number of parameters involved in the inner loop. Okay, so this is the first types of like ways to reduce the number of parameters to overcome the task overfitting. And to overcome the task overfitting, there are still other ways. So one way, like maybe like called like meta dropout. So this would be mostly more like a dropout issue, a dropout in the traditional neural network. So here we will see that we have a main network, which is called also like a base network, and we input the X, we feed the X to different layers, and then feed into the follicular layer. Besides this, we will also involve some noise generators to generate some noise. It seems like in these models, they will inject some adaptive noise. So this noise could be adaptive because it still depends on the samples for each task. Here we could see like we will also at the same time we will input the X into the noise generator, and it will generate some noise and to be added into the hidden representations. So through this way, it could be like models as could be regarded as one types of dropout issues and to add some noises. And let's see some results of it. We can see like for example like a memo. So we can see like here there's a decision boundary. So the decision boundary maybe cannot distinguish different classes very well. So for example, here is like the training samples and these are both are training samples, maybe from two classes, and there are still some perturbated training samples and also like the test samples, like there are a lot of test samples and there are perturbated training samples. And we can see compared with memos, the meta dropout can be better to distinguish different class samples from different classes. So this is another way to like overcome the task overfitting. So there are instead of the task overfitting, so let's see the meta generation. So the meta overfitting usually is much more challenging problems than task overfitting because like some traditional ways to overcome the overfitting issues could be also used like in meta learning to overcome the task overfitting. So the overfitting issues within task. However, like the difference between like a meta learning process with the traditional learning process is like it will have a lot of meta training tasks. So so if we want to like overcome the overfitting issues across the different meta training tasks, so things will be different. So let's see why it is very easy to overfit. Here is one example. So this example is for the drug activity prediction. In the drug activity prediction, the higher we evaluate the R-square values between the ground truth and the predicted value. And here we would like to see the larger R-square would be better. So in this figure, we can see like here are meta query samples, and also we have some meta chain spore samples. We can see the learning initialization is easier to overfit on the meta chain query samples. So we can see the blue line, and the better performance was on the meta chain support samples. See the green line about that. And besides this, we can also see there are a large gap between them. So we call it like inconsistent behaviors. So there are several ways to overcome the meta overfitting issues in recent years. So one type of methods is to passively impose the regularization. So the first method is called like TAMO. In the TAMO, we can see that we will add the regularizer and the model initialization theta. Here is for the model initialization. This is for the model adaptive parameters. And this is a traditional loss of the like gradient-based meta learning. And we will get another loss, which is add some constraint on the model initializations. So this constraint is more like is called like an inequality measure. So we want to use this constraint to encourage the similar behavior across different tasks. So we want to like reduce the inequality of the model initialization on different tasks. So we would like to make them more similar and to like reduce the overfitting issues. Because like sometimes we have more and more tasks, maybe a lot of tasks more similar, and this initialization would be overfit to these types of similar tasks and cannot be generalized very well to the different new tasks. So these models want to reduce the inequalities generated from the model initialization parameters. So the other work is called like MMO, published in IKEA 20. And in this work, we can also see these figures. They have several meta training task 1, meta training task 2, and like meta training task 3. If I adapted meta testing tasks would be very well adapted in this figure, so it can fit these 3 points. However, if we say memorize it, or say learn or memorize to all meta training tasks, or meta training task 1, task 2, task 3, or they will have such a curve of each. And if all memorized, it may not be adapted to the meta testing tasks. And so we cannot get a better like a curves on it. So on the meta testing task. So how to avoid it? So they're assuming that the overfitting issue is generated that if we have some meta training trained models, so like the prayer here I defined it as M, so like the prayer like here we also like the model initializations, and if we do not like use the training set or support set in the meta testing task, for each meta testing task it has a training and support, and if we do not use it, we will use the training to do the adaptation. But if they found that the training data set may not be very important if the memorized in the meta training tasks. So their goal is they want to maximize the mutual information between like the training samples given the testing sample in the meta testing task, and the training samples, all the training set D, and also the predicted value Y. So they want to maximize the cross entropys between Y star and the D. So it can be regarded as, so they want to make the training set in the meta testing tasks more important. So it could be still be adapted in the meta testing tasks. So how to achieve these issues? So they design one KO divergence between different parameters and to add some regularizer on it. So both of those algorithms, they want to passively impose some regularizations to reduce to overcome the overfitting issues in the meta learning process, especially on the meta generalization. Here, one question is that is there any active ways? As we know, some active ways like some task augmentations are very popular in recent machine learning research. So can we involve this information in the meta learning process? One intuitive way is that we want to using more data in the meta learning procedure. As the most straightforward way could be we can simply combine the support set and the query set, because if we only update by using query set to do the out loop, so whether we can combine the support and query. However, we found also support gradient norm is very, very small because we do the inner loop, and which will causing the support gradient norm is negligible. So it may be not change too much if we simply combine support and query. Thus, to optimize it, so the MetaMax is proposed. So in the MetaMax, our goal is want to do the mix up between the support set and the query set. So in the out loop, so here we show the loss functions in the out loop. And in the out loop, instead of we use the query set to do the out loop optimization, we will use the manifold mix up for each task. So for each task, we will randomly select one layers, and through these layers, we will do the manifold mix up and to get the updated parameters, so the x mix and the y mix. So and then we will use the x max, x mix, and y mix to optimize the parameters. So let's see some performance of like active ways. So this could be a very simple active ways, but it works very well. So let's see like one example. We can use this example. This example is from the drug activity prediction. Here is the before meta mix. We will have a large gap between them because like the performance gap between the meta training support and the meta training query. And later we will use like the after we apply the meta test, the meta mix, we could see like the generated gap would be very small. So and also the performance on the meta validation queries are still improves. Okay, so this is just to see that the power of like use the meta mix. So the meta mix is very simple ways, effective ways to do that. Also, we want to see some results of the meta mix by see some image classifications. Here we list some base models like MAMO, MetaHD, TNet, like ANO. And in these ways that we also added the meta mix to different organisms, and we can see that it can significantly improve the performance on the image data set. And besides this, we want to see like the memo and the meta mix, so they may have like we plot the similar figures as the meta dropout. So this could be like the distribution boundary can be better distinguish like different types of organisms. So the different types of samples. Okay, so this is another challenge I want to mention is about the meta overfitting. So in the challenge part, we mentioned like the task rigidity and the meta overfitting. And in the last part, I want to mention some results about online meta learning. In the online meta learning, here we can see we have one task pool. And through this task pool, we could get a new task. So in this part, the learned prior, for example, like the model initialization in the model in the gradient-based meta learning, so it would be fixed in the meta testing part. So we learn the model initialization in the meta training process, and then we apply it to the meta testing process, and like to want to improve the generation. But we only consider the tasks in the meta testing tasks, and we fix the model learned prior. However, a more realistic case is like a sequential learning. In the sequential learning part, so we will have like for example, like our human learning, like we first learn from walking and then running and swimming and scaling and a lot of different tasks in a sequential manner. So in the sequential manner, so the learned priors would be continually adapted continually adapted. And thus, we will consider the performance of the sequential manners, consider the performance of all tasks. Okay, so this could be a more realistic settings in the online meta learning. So in online meta learning, let's give some formal definitions. So first, we will like given the regret minimization in online learning. So in online learning, we give the regret things by first like calculating the parameters of each step, and then choose the global minimization over the all times. And similarly, we will involve another network in the online meta learning, the regret of the online meta learning, because like we can see like so you could be like for example in memo could be in the gradient descent on edge, and then we will revise this regret definition in the online learning to online meta learning, and the code is generation bound, which is relevant to the log T. So this is just for a definition of the online meta learning. So let's see if we want to apply it. So what we can do. So here we want to show that how to apply memo at each time step to achieve the performance on online meta learning. So here we can see that, for example, like we have the online meta learning with FTML in the proposed model. So we will have one task buffers. In this task buffer, we will import different tasks, and we would like to do the meta update on the different parameters. In the meta update, we will like retrieve some informations from the task buffers, and then we do the meta update. And we after that, so we got the current parameters, which is the meta updated after meta updating, and we will get the updated parameters, which covers the historical knowledge and also the current knowledge, because it has a task buffer. And sorry about that. So the video is unstable, and then we will try to do the inner update for the specific tasks. And so this is a basic procedure of applying memo at each time step. So the meta update would be a whole memo process, which will sample some training data and validation data from the current from this task, and then do the memo on it. Okay, so let's see like how we want to have it in see some experiments of it. In the experiments, here we just show one experiment about the rainbow MNIST. In the rainbow MNIST, it's changed the MNIST with shape, color, and size. So after change that, we finally get 56 tasks, and the tasks are feeding into the model sequentially. And since it's like more like a homogeneous task, because most of samples within each task are very similar, and we want to compare some of the task learning efficiency about that. So the task learning efficiency could be regarded as the amount of task data needed for 90% of accuracy. So this part could be like we use FTML compare with, for example, the train from scratch and train from the all of the data and FTL. So here it's obviously we found that the FTML performance best compared with baselines. For example, like a chain of each task and performance the worst. And the train from scratch also performs better. So train from scratch also covers a lot of data samples. And we can also see the task performance after 100 data points. So the FTML also works very well. And the last thing is for the task and the performance is that which covers a lot of data samples for each task. And here we see that the FTML also works very well compared with TOE, because TOE be compared with the from scratch, because from scratch they use a lot of data samples of it. So it can also works very well. So this is one preliminary work about the online meta learning. So next I will introduce another work is about the online meta learning with knowledge structuring. Let's see, this is just for the framework of online meta learning. So we have a lot of homogeneous tasks, and then we generalize some knowledge from it and learn in a sequential manner. However, one more complex way could be like we have a lot of different versatile tasks. And this task will be summarized to different parts. Here, for example, in the middle part, we have some sports tasks. In the top is we have some language tasks. And in the middle, we have some like logic tasks. And in these different parts of different tasks, and it can be like, as we discussed before in the task heterogeneous part, it could be like organized to different like clusters. So how to tackle with these problems if we have more versatile tasks, and how to like structure it, and can we like use previously we discussed some ways of task representation networks. Can we still use it? So this is some remaining questions. Or in these different questions, we could see like the online meta learning with knowledge structuring. So as we discussed before, we use some task representation networks to learn the good task representation, and then like using these task representations to customize like a different model initial parameters. However, it's usually hard to train from scratch because like we input the tasks in a sequential manner. So the task one, if the task one arrives, so it's very hard to train a very good task representation network by just only having a few tasks. So we are thinking that is there any like some other structuring way? Motivated by the knowledge structuring, like in the knowledge blocks and in the principle of compositionality, we are thinking, for example, here are a lot of building blocks. So using these building blocks with different like instruction, we can get different shapes. Here we have some buildings like vehicles. So through this way, we can think that whether we can like in the online meta learning part, whether we can like increase the number of parameters, increase the size of models with more knowledge blocks, and then we would maybe select one path from that. Here we can see like the base models would be disentangled to knowledge block based net. So for the base net, it will be disentangled. For example, here in the layer 1, it has 2 blocks. Also in the layer 2, it also has 2 blocks. And given one task, maybe we can find a path within this knowledge structure. So here for task 1, it will select the left the second part, the second block of task of layer 1, and select the first block of layer 2, and then construct one path. So similarly, in task 2, we will select the first one of the layer 1, and also the same first one as layer 2, and construct one path. So to apply these models, there are 2 steps. The first one is the meta-knowledge path reconstruction. So in this part, we will consider, because task stream could be heterogeneous. So in the heterogeneous task streams, we would have first have the knowledge-based block-based base net. And then if the new task is very similar to the old tasks, so we could reuse the previously learned like paths. Because like, for example, task 1 could be classified maybe 3 different birds. Task 2 also classify 3 very similar birds. So the task 2 could also reuse the path of task 1. However, there are still, in some heterogeneous case, there are still have a more complex case, in that we have maybe heterogeneous tasks. Task 1 is to classify 3 different aircrafts, task 2 to classify 3 different birds. So they are maybe different. So we want to maybe, if the task 2 come in, we want to explore some more knowledge blocks, and which can be also find a pathway on it. We regard this problem as a block search selection problems. So it could be like a structure search problem. So in these structure search problems, it's quite similar to like the neural architecture search. So instead of searching for different structures, we select for different knowledge blocks. And for each task, we will adapt its parameters by layer by just do the inner loop on each, and then get its hidden representations. And here we use another parameter always to define for the probability of each. And here maybe we will the high probability to explore a new knowledge block. In this part, we will finally do the parameter update on each. So we're using the task adaptation and then go back to optimize the parameter theta and the selection parameter O. And finally, we can get a knowledge pathway, and after the searching process, by selecting the maximize the parameter of O in, and to get the corresponding knowledge blocks. After that, we will use some block updating and task adaptation. So in this part, we will have like the base net, which has 2 blocks, and we select, so we explore the block in the layer 1 and with layer 2, and then have the old block, use the old blocks in the layer 1. Or through this way, we will select some relative tasks in the task library, and then use the block meta update on each. And in this block meta update on each, we would like to maybe update the selected blocks in this pathway use the related tasks. So this updated way is also like applying memo on each. And at the same time, we would like fine-tune for the current task. To fine-tune for the current task, we will like using the selected logic pathway and then to applying fine-tuning on each and to maximize performance on the current task. Similarly, the performance is also evaluated in the homogeneous task stream, which is totally similar as the FTML, the Rainbow MNIST, and also evaluated in some heterogeneous task stream, which covers 3 fine-grained image classification subdata sets, the flower, aircraft, and fungi. So each specific data set has 100 classes with 20 non-overlapping 5-class classification tasks, and in total, it has 60 tasks. Compared with the performance, so the OSML can achieve better performance compared with the other baseline models like the FTML, like DPM, like also fine-tuning. And in this part, we also compare some learning efficiency on it. We can see that the OSML achieve better learning efficiency, for example, compared with FTML. So we may need less samples for achieving 90% of accuracy, because the homogeneous data samples were very similar and which can have a hard threshold to achieve the accuracy. How many samples to achieve the accuracy? 90% of accuracy. In most scenarios, OSML works better. And for the heterogeneous data, so because the different tasks may have the totally different performance, so it's very hard to have a hard threshold. So instead, the learning efficiency would be evaluated by changing the number of data for each task. So OSML is also achieve better performance. And in this part, so we also do some model analysis on it. First, to analyze the model capacity on it, because we in the OSML it increase the number of knowledge blocks, so which will increase the number of parameters in the base model. So if we increase all the models maybe to the final size of the OSML, if they train from scratch, we will just make them as large as the final steps of OSML. So but OSML still achieve better performance. Or in addition, for the selected ratio of blocks, so like different layers, and it can see that some layers, maybe the block 0 of layer 1 belong to aircraft, block 4 in the layer 1 belong to aircraft also, like layer 6 also belong to aircraft, and also block 0 belong to layer 3. And both things are demonstrated that it can work through if they have some selected ratio of blocks. So this is some interesting findings. And for some other methods, which can also use some Bayes methods, use also like continuous without tasks. So this is like unsegmented tasks distribution. So we need to detect the checkpoint and to then to do the adaptation, and also like to do some variable short adaptation for the online meta-learning. So both are like other online meta-learning studies. So this is the first part of the meta-learning. In this meta-learning part, we discuss 2 types of meta-learning methods, and then the gradient-based meta-learning and metric-based meta-learning. And we also discuss 2 challenges in meta-learning field, so the task heterogeneity and the meta-overfitting. Finally, we discuss some preliminary work of online meta-learning. Okay, now let's move on to the part 2. So in the part 2, we'll discuss how to leveraging the domain knowledge in the model. So here we were using the domain knowledge to guide the loss function, also to design the models. So because like if we only have limited data, so domain knowledge could be one of very important issues to integrate it into the model and to provide some prayers. So here in this part, for example, if we want to like predict a Bose trajectory, so what will a data scientist do? So in this data scientist, so they will throw the ball as many times as possible, and we have a lot of we can collect different trajectories about that, and then we could build a machine learning models to do that. For example, here we have several features like mass, like current position, like initial position, like force, and then we would use this features to import it into a machine learning model, and then it could be get the next position. So this is a typical way in data science, and the data scientist will do to predict a Bose trajectory. And if we also want to predict the Bose trajectory, what will be a real scientist do? Okay, let's see. So for the real scientist, it will retrieve some laws in the physics. So here, for example, like this is the Newtonian physics for babies. And they have the Newton's first law, the second law, and the third law. And through these physical laws, and it can like do a lot of cool things. And for example, you can predict where the balls will land by using different physics laws. So this would be a typical scientist, real scientists do, because they have a lot of like laws, physical laws to help us to to do the prediction. So the question is, can we like combine the machine learning model and the domain knowledge models? In the machine learning model, it will learn from the data, so you have features and you will output the label. And in the domain knowledge models, so they are totally based on the series. And if we can combine them, so maybe combine some domain knowledge model and the machine learning models, the domain knowledge model could be provide some prayers for the machine learning models and then cross label. Okay, concretely, so we will cover two parts. So the first one could be the loss functions designs, and then for the using domain knowledge for the model design. In this loss function design, so the first example could be like if we want to leverage domain knowledge, so there are maybe a loss could be construction, or if we for the loss construction of a typical machine learning model is for the to calculate maybe the distance between the predicted label and the ground truth. And so in the residual modeling, so our goal is to predict the gap between the domain knowledge model, between the prediction of the domain knowledge model and the machine learning models. And let's see that we still have the features, and these features could be inputted into could be fed into the machine learning models and get its prediction. And similarly, features can also be fed into domain knowledge model and get the prediction. Then both prediction values could be added and get the final prediction models. So the YDK plus YML. And here we will try to like use the DK as a combination as part of the machine learning model. So we can see that we will use DK to help the machine learning models to do the prediction. So the question would be like, is there any guarantees behind this? So yes, we also found some guarantees. So it seems that it performs better than purely using the domain knowledge models, and it could be better than purely using machine learning models to do the predictions. But to be more specifically, here are one examples. So in this example, the goal is to predict the temperature of different places on the Earth. So if we want to do things, what will we do? So the first part, we will like calculate the heat from the sun, and here calculate the amount of energy that reaches the Earth according to the distance. And the second one would be like calculate the Earth's heat absorbed by the Earth, because different locations in the Earth may have like different energies. The third one would be the calculate the result, the temperature, and it will be assuming as Earth is a perfect emulator and it emits the same energy as it absorbs and converts the heat to temperature. So use the Stephen-Boltzmann law. So we have using the different physical laws. So we calculate some features or like some informations, and then feed into the physics law and then to get the temperature. Okay, let's see. If for the machine learning models, what we can do is that we will collect a lot of data, for example, like the data from October, from November, from like December, and we will feed this data to the machine learning models, and with some features. These features could be the month, the year, and the location. And after we feed it, and we can use it to predict the temperature. So since in the machine learning models, so the prediction values was totally learned from data. And in the domain knowledge models, so the performance is based on theory. So this theory here is for Stephen Boltzmann law, and it will evaluate the temperature on the Earth based on its relative position to the sun. So here we will have a lot of more information about that. And if we combine them, maybe using the domain knowledge model and the residual part of the machine learning models, what the performance is. So here we see the performance is very well. So if we only have we use the mean square or root mean square error to evaluate the performance, the smaller is better. And we will using the domain knowledge models, machine learning models if we combine both machine learning model and the domain knowledge models, the prediction is very well. Because if we simply use domain knowledge models, even because domain knowledge models is based on a lot of assumptions, so which may be a little shift. So compared with real world cases, so we can also use our machine learning models to give a lot of hints to help us to predict the performance. So that's adding the residual works very well. And to be more specifically, we show some cases like the predicted results with different models. Let's see the ground truth, maybe different colors represents the temperatures. The higher, so the red one would be hot, and the blue would be cold. And then if we just simply use domain knowledge models like here, and we just using the Stephen Boltzmann law to do that, and maybe it would be too cold in the north. And if we simply use the machine learning models to do that, so most of the regions would be very hot for that. So, but it would be better if we can combine them together, so to predict the domain knowledge and the machine learning models, and we maybe can find a very good performance here. We see that the south would be hot and the north would be relatively cold. So which is performs very good compared with simply use domain knowledge or simply use machine learning model. Okay, so this is one typical example of that, how we use the domain knowledge to guide the loss function by using the residual by calculating the residual part. So using the residual modeling. And the other type is we can maybe using the domain knowledge as some regularizer. So here we have the first for the machine learning models, we have the prediction as the loss function with the y machine learning model label y, predictive label y, and the ground truth y true. And we will involve the machine learning model MDKX into the regularizer and compare with the machine learning as predictions in the YML. So the GS represents a measure of consistency between the domain knowledge and the predicted label. And the MDK would be a domain knowledge transformation of feature KX. Here one example. The example is that we want to incorporate the energy conservation modeling of lake water temperature. So here the goal is to predict the lake water temperature. So here we have several features. The features could be meteorological drivers. So we have drivers have a lot of different types of features collected by the scientists. And then we want to output the lake water temperature, so which is called the in temperature and the out temperature. So the if in would be like the incoming energy fluxes, and F out would be outgoing energy fluxes. So the energy fluxes F in and F out include the long-term and short-term radiation, sensible and latent heat fluxes. So we will like here we will want to predict the lake water temperature. So for a specific example is that we want to how to incorporate the energy conservation. Let's see that the lake we will involve the lake theorem energy budget. So it will be a balance between the incoming energy fluxes and high heat loss from the lake. So this would be a mismatch in losses F out and the gains in Fe. So it will change the lake thermal energy and will also change the lake temperature Y. So this would be a very useful information to be involved, because like we will like using this could be like guided, provide some like ecological informations to guide the machine learning model training process. So here we want to define the domain knowledge based models is that we use heat and predict heat with the trend of the lake thermal energy compared with the mismatch in the F out and gain F in. So it will be model the change of the lake thermal energy. Okay, so this is we define the domain knowledge based loss, and this could be integrated into the prediction models to help us to like, you can also regard it as it can correct the prediction and also to make the prediction more accurate, and also like constraint the search space of the parameters. Okay, so we can see like the domain knowledge based loss penalized if the model predicts an impossible energy change to a daily scale. So in this part, the domain knowledge based loss, with the domain knowledge based loss, we can see the performance in like Mendota. And in this part, we will using the IMC to model it. Here we show that the difference about that. If we simply use like the iron, so maybe its performance is very bad. So, but if we simply use like the physics models, so we can better capture it. But finally we will like get the machine learning models and the PGN. So we can see it's not a perfect match because this equation is built based on our current body of knowledge in understanding physical systems. But in reality, so because the mismatch is caused by the, in reality there are many minor physical factors that are ignored, so or missing from this equation, so which will cause the mismatch of it. So this part I discussed some methods like to integrate the domain knowledge into the how to design the loss function. In the next part, we will introduce some knowledge about how to use the domain knowledge to help the model design. The first example would also be like we want to model the lake water temperature. If we want to model the lake water temperature, we will try to encode in some intermediate domain variable. So let's see that because some intermediate physical variables would be introduced into the recurrent neural network model to capture the energy fluxes that are driven the temperature change. So the energy transfer process could be energy fluxes, which has some intermediate physical variables, and then we get some lake thermal energy, which is also like a physical states, and then we can get some lake water temperature. So we add the model outputs. So we see in the standard iron flow, it will be hand input and then feed into the LSTM cell and then feed into the next part and also get some LSTM state. So in the energy flow, so if we have the temperature Y and it will be feeding into some physical state and get some physical state with some physical variables. These physical variables could be used as some energy fluxes, radiation, evaporative heat. So these variables with the state could be fed into the next part to get the physical states and physical variables. Physical variables also generated from the features. And if we use the physical-based loss, so it will be like we will use these physical states and to incorporate with the model with the y with the predicted temperature. Let's see also see about that how to incorporate it. So here we will extract some intermediate physical variables for the upstream segments, and this is and then we will like model the relations between some physical equations, and these physical equations would be integrated into like such and the loss function. So the amount of water adapted from a segment and its water temperature can directly impact the change of water temperature from its downstream segments. Because like we can see, like we model the different segments. Like here we use different LSTM cells to model the different segments, and then go different segments will be combined to the mainstream segments. So the water temperature will be interact, and then also would be involved into the process. So in this part, we will here we discuss some how to encoding some intermediate domain variables by using one example as modeling the lake water temperature. Here are some other domain-specific knowledge. Here are some other ways to encode some domain knowledge. For example, in the example 1, so we can predict the ages from the neural images. So here we have the feature map of images and do some different convolution layers. And here is the beginning layer is added to segment the input bring volume to different regions. And each region can treat it as a separate channel, and the convolution filters use different parameters for different regions. And in the example 2, so for the generative models, they can generate some super resolution through the flow. So, and here we will design 2 discriminators to model the spatial and temporal aspects respectively. So, and a new discriminator network and a new loss function are proposed to preserve the temporal coherence in generative physics-based simulators of fluid flow regions. So here is that we use the generator models G and to get some generated the figures, and in the space values we would use some ground truth or physics-based simulators, because if you use physics-based simulators, you can also get some ground truth images and to add it as some loss functions and to guide how it's generated. So if you can use some ground truth to guide the generator and the discriminator, so it will be make a generator and discriminator more accurate. So it's the G for the generator, and the DS and DT are both for the temporal discriminator and the space discriminator. Another part would be some the neural architecture with physics priors. So our goal is to learn a function with some hypothesis space, usually a neural architecture search about that. So the omega would be the network parameters, and alpha would be architectural parameters. And here we design different part of it. So with some operation set like Fourier layers, skip collection, and some ways. So these are very common things about that. The key contribution of that is that it can involve some physical equations and physical laws. So here we can see this physics involved would be a mixed operation set here, and maybe we can select that whether we need to use Fourier layers or use some physics forward or simply use the gate collection. So if we use that, we can maybe find a better neural architecture structure. So we know where we just use physics rules, and where we use the neural network and to help us to do the prediction. Okay, so there are still other reasons for incorporating domain knowledge into machine learning model. For example, encode PDE into the kernel or Gaussian process regressor, and monolicity preserving structure in the machine learning models, and this also using some auxiliary task learning. So by using additional tasks for the discriminator of networks in a generative adversarial network to satisfy certain properties of particle interactions for production of jet images of a particle energy. So maybe different physics rules could be integrated into the current machine learning models and can help the learning process of the machine learning models. So this is the second part we want to discuss is about how to use domain knowledge to choose a loss function and the model design. Okay, so then Professor Fei Wang will discuss some applications from the healthcare domains.
Hello, everyone. My name is Fei Wang. I'm currently an associate professor in Department of Population Health Sciences at Weill Cornell Medicine in Cornell University. And it's a great pleasure to introduce this tutorial together with Huaxiu and Jesse. And I'm going to talk about the small data learning techniques in analyzing electronic health records. So we have heard a lot of stories and techniques from Huaxiu, and I'm going to first introduce why do we need small data learning in EHR, and what are the promising techniques, especially the ones Huaxiu has already introduced. It could be useful in this scenario. So first, let's review about some of the success stories about machine learning in different applications in recent years, such as the Go game, the autonomous driving, and speech recognition, and more recently GPT-3. In all those scenarios, we have big training data to train a fairly complex model, and the model demonstrated really good performance in their respective applications. And so then because we are talking about small data, but what is a big data? So I'm just copying one figure from the internet. So this is just an example of how much data is generated within every minute. Of course, it cannot be exhausted in such a simple figure. The data could be much more in all those different domains, like videos, like text, like speech, and so on and so forth. And we know that the size of the data is growing bigger and bigger. We have from megabyte to all the way to now I think we have already have this word brontobyte. I don't know how many of you have heard of this word, but then what is the next byte? So why they are important? And also a related question is, how big is big? So before we think about how big is big, so let's think about the big models. So what are the those models that have demonstrated the successes I have showed in those different applications? Here I just showed some big machine learning models, especially deep learning models, for successfully analyzing computer vision data, especially images like the AlexNet, where we have 62 million parameters, and we have what is this, ResNet, we have 11 million parameters, and VGG, we have 138 million parameters, and also Inception version 3 will have 24 million parameters. So all these models are really big here. Big is really measured by the number of parameters contained in the model. But we know it's not just the number of parameters, but also how those different computing cells, like the convolutional filters and pooling layers, are connected with each other. So this makes these models, number one, big, number two, really complicated. So in order to learn such a huge model, we can imagine we definitely need a large amount of data. Otherwise, there's the problem is under specified which means that your model have more degrees of freedom than your number of samples, and then there could be a high risk that your model won't generalize well. So that's why, from one aspect, we need big data to train those big models. And same thing for medicine. So we have all different kinds of data. The central entity for medicine is, of course, human, and around the human we have a large amount of heterogeneous data entities around them, like electronic health records, clinical notes, physiological signals like ECGs or EEGs, like videos, like dialogues, like biomedical literatures, treatments, and neural images or medical images. And I'm sure a lot of you have heard of this word, precision medicine. So what is precision medicine? It's really, we want to like develop tailored or customized treatment with respect to individual patients. This notion of precision medicine really reflects a new paradigm of treatment development, because in the past, people usually talk about one-size-fits-all drug, where for every disease, we just aim at, developing a single drug that can treat the whole disease. But because of the complexity of the disease and heterogeneity, it is unlikely to happen. So how can we really develop tailored treatment for individual patients? Really needs to have a comprehensive understanding or characterization of the patient health status. So as Francis Collins, who is the director of NIH, envisioned in his perspective about precision medicine, so we really need to integrate data from all different scopes and aspects, including molecular, genomic, cellular, clinical, behavioral, physiological, and environmental factors. And that's basically, you can have a sense on like number one. So for healthcare or medicine, we also have complex data across all different modalities. And number two, the question is whether these data are big or small. Of course, in terms of the size, you can think of in the past when people use like conventional statistics or machine learning approaches to analyze patient data. Typically, a cohort is just tens of patients or hundreds of patients. If we have thousands of patients, we say it is a big data set. But now, clearly, it is no longer the notion. We can easily have like millions of patients' records. But does that mean the data is big? So in this talk, in this part, I will mainly focus on electronic health records. For most of you know, so electronic health records is a systematic collection of patient, individual, or group electronic health information, including like demographics, diagnosis, medications, lab tests, and procedures, and so on and so forth. So every time when you pay a visit to the clinic, the doctors or nurses type a lot of things in their either laptops or iPad, and the system sit behind those computers or mobile devices or electronic health record system. And in recent years, because of the rapid development or deployment of the electronic health record system, so a lot of hospitals have already deployed such systems. So a large amount of patient EHR data sets have been accumulated, which creates a unprecedented opportunity and also a basis for us to develop advanced machine learning techniques to analyze them. So there are lots of papers published, targeting this goal. For example, this is a paper about using deep learning to analyze EHR and perform risk prediction. This is about analyzing patient EHR to build a specific risk predictor for acute kidney injury. And there are many, many more. So let's first look at some of these papers, like the first one. So this is one of the very first papers from Google in collaboration with UCSF and the University of Chicago. about building deep learning models on electronic health records to predict some risk, to predict some clinical risks. And this paper is very impactful, as you can see from its citations so far. There are 3 tasks that this paper is looking at. So one is in-hospital mortality prediction, and the second one is hospital readmission prediction, and the third one is length of stay prediction. So for all those 3 clinical risks, so there are widely deployed clinical risk calculators, which is typically based on simple clinical features, and you can create a simple linear model like logistic regression, or a scorecard, like if you have this feature, you get 1 score. If you have that, you have 3 score. And then finally, you add up all of them together, and you got a total score, and you have a threshold. If the score passes that threshold, you have high risk. Otherwise, you have low risk, and so on and so forth. So I just listed some of the baseline algorithms that this paper is comparing to, which are typically those clinically used risk predictors. And the deep learning model that this paper built is a ensemble of 3 deep learning models. 3 models. So one is weighted recurrent neural network. One is feed-forward neural network with time-aware attention. The other is boosted decision stops. So all those 3 models are chosen for specific purpose because they have their own specialties on working with specific scenarios. And this is actually the performance on the different tasks on 2 different hospitals when we use different models to predict the different clinical risk. Where the first row is for under each task is actually the performance of the deep learning model. And the second row to the 4th row are some of the basic baselines, including the clinically used risk calculator or some handcrafted features based on which a logistic regression-based risk calculator is trained. So we can see that from this performance, you can see, although with this complex model, so we don't see too much improvement if you consider the complexity of the algorithm for this model compared to those baselines. So that's a kind of like a surprising observation, because it is very different than we have observed in like image or speech or natural language, where deep learning model typically can improve the performance by a large margin. And actually, there's one research from my lab. We also have a similar kind of observation in another different study, where we are looking at by leveraging longitudinal claims data, can we build deep learning models that can accurately predict the readmission risk of patients with COPD. COPD is stands for chronic obstructive pulmonary disease, which is a pretty prevalent chronic lung disease. And readmission, which means that the patient, after he or she is discharged from the hospital, he or she came back within 30 days. So a lot of the times, those readmission can really be avoided, and they can be harmful to the patient. And so, like the Center for Medicare and Medicaid Services, the CMS, they explicitly penalize the hospitals with higher readmission rates. So that's why predicting hospital readmission is of a huge interest to not only the patients, but also for the hospitals. And in the past, this there's I mean, not no perfect predictive models that perform this task. I mean, the performance is not so good. So we hope here is a very good scenario that we can apply or show the advantage of deep learning models. And we investigate a whole bunch of different variants of deep learning models. We start from the patient data representation, from vectors to matrices to sequences. And we also pick different kinds of features, including the knowledge-driven features, which are typically used in the conventional clinical risk calculators, and also some handcrafted features according to domain knowledge, and also to all the data features available within the patient records. And but the problem is that with all different kinds of variations, we also tested like different, because the patient records is longitudinal, so we aggregate them according to different resolutions, and we can also embed those different events using different embedding method. But no matter how we change the settings, we don't really find that deep learning model can really beat those conventional models by a large margin. That is also similar to what has been observed in the previous paper. And this brings us to sit down and think about why this is this is the case, and what caused this. And in order to understand this, so we first think about some of the failure cases of deep learning models. So number one is this: if you recognize this big white truck, this is actually the first car crash of Tesla when using the autonomous driving system in 2016 in Florida. So the autonomous driving system, which is essentially a computer vision system that didn't recognize this is really a white truck, and so the car still drives in full speed and crash. So this really, later on people figure out it is because this scenario has never appeared in training data of the autonomous driving system. And the second thing is about the recent very popular GPT-3 model, and this is from this paper from Gary Marcus and Ernest Davis. And they basically give a paragraph for GPT-3, like, you poured yourself a glass of cranberry juice, but then you absent-mindedly poured about a teaspoon of grape juice into it. Looks like okay. You try sniffing it, but you have a bad cold. You can't smell anything. You are very thirsty. So, and the text with bold font are what is automatically completed from GPT-3. And so you can see it says you drink it and you are now dead. Clearly, it is not the case. But why is that? It is because, as the authors have pointed excellently in their paper, in their essay, they learn about these models. They learn about text and how people use words in relation to other words. So it's kind of like a massive cut and pasting. So in this case, the reason why it's imputed, like you are now dead, is because it is frequently connected to the way of presentation for the paragraph before. So it is not really figuring out the semantics as a human, but really it figures out the patterns on how like sentences and words and even paragraphs are connected to each other. So they learn that pattern, and that's why they produce this kind of completion. And so from these two, we can kind of see that. So deep learning models, they're big models, as we said. They can fit in your training. They can fit your training data really, really well. But if you have limited training data, which means that your training data cannot cover all the possible variations or patterns of your sample space, or your problem is too complicated such that there is no way that you can find enough data to cover the entire problem space, then you are facing with actually a small data scenario where if you fit your model to your training data too much, then the model cannot really generalize well to real-world scenario. So unfortunately, that's the case for most of the medical or healthcare problems. So number one, you cannot have too many data samples from individual patients because typically we just have access to the clinical or the EHR records of the patient from a single hospital or a single region or a single state, and so on and so forth. But the disease, which is a problem space, it is usually super complicated such that human cannot even understand. So that makes the problem essentially a small data, but we want to fit a big model. So small data, big model problem. So in that case, it is, not surprising that those models cannot generalize well. So they kind of like perform similarly as those simple models, like what have been compared in the baselines in my two examples before. So then how should we make or develop appropriate machine learning models by realizing this scenario? So I here list or introduce several important directions. So number one is you should understand your data better. So this understanding is not understanding from data scientist perspective, but really we need to work with domain experts. In EHR case would be the clinicians to work together and understand what are the clinical processes or operations involved in collecting the data. Then that can a lot of the times help us to build better models. This is an example from Harvard, an excellent example where it shows that a lot of times when we analyze EHR data, when we use or want to analyze lab tests, we usually take the lab test values. But what this paper shows is actually the time when a lab test is ordered sometimes can be more predictive of, in this case, is the 3-year survival rate of the patients than its actual value. What it shows is that if a white blood count test is ordered at 4 a.m. for the patient, for a specific patient, even if the WBC result returns to be normal, it is more predictive of the 3-year survival rate than if, let's say, we have ordered a lab test, the same lab test for the patient at 4 p.m., even if the patient is having an abnormal value. This is because the nobody gonna order such a lab test at 4 a.m. for no reason. So there must be something happen, and the clinician observes something, so he or she orders such a procedure. So basically, this suggests that if we know this, then we know actually the actual time stamp of the lab test is usually very important in this context. And but a lot of the times when especially we leverage like RNN type of model to analyze EHRs, we only care about the sequentiality instead of the exact timestamp. So that's gonna lose some important information in terms of risk prediction. Another is model under specification. This is not surprising because, as I said, this is a small data scenario and we are fitting a big model. So there definitely could be multiple fits that you can map the same input to the same output, but those different fits leads to different models that generalize differently on the testing data or the data where you're going to deploy those models. And this is a very famous paper recently from Google, and there are lots of news report related to this. And so people are worried about those model under specification. But like Huaxiu has introduced all those small data learning problems. So this is where those small data learning algorithms can be helpful So I am envisioning some of the techniques like transfer learning. So typically we won't have enough medical image to train a monster image computer vision deep learning model from scratch. But if we can fix the feature extraction layers, but fine tune the final layer, or treat what has already been trained for all the layers, those parameters for all the layers, and leverage it as a warm start to fine tune, just using the local sample, medical image sample. Then this has been demonstrated to be able to get good performance. This is like we transfer the knowledge that this model learned from general image data set like ImageNet to the medical limited medical image data set. And we also have a paper, this is in KDD 2 years ago, about for certain conditions, some of them could have fewer sample size, some of them could have a larger sample size. So we use a meta-learning type of technique to transfer the knowledge from the prediction, the disease condition where we want to investigate with larger sample size to the conditions with a smaller sample size. And also, as I said, because of the fragmented nature of medical system, the patient populations are in different places, in different hospitals, and because of the sensitive nature of those patient data, we typically cannot simply combine them all together and train a model. But how can we still leverage the useful information in all those patients' records without releasing the privacy information? So federated learning offers a very good alternative to solve this problem, and it has been demonstrated to be successful in quite a few different scenarios. And also, the other thing is electronic health records just encode the clinical information of the patient, but there could be other informations reflected in other data modalities as well. So if we can integrate the information from other places together with the longitudinal clinical records, that can help us to better figure out the patient health status and perform a better, let's say, risk prediction. And this is an example we worked on, like Parkinson's disease onset prediction based on the longitudinal clinical records and brain images. And we showed that by combining the information from two modalities, it can lead to the best of prediction performance. And also, this is a mortality prediction example in ICU for patients in ICU by combining both EKG signals and the clinical records. And the other thing is model interpretation. So when we talk about, so in a small data problem, in order to like alleviate or avoid a model or mitigate a model under specification. So another good way is to translate those models into human understandable rules so that we can easily see if it makes sense or no, and those rules or knowledges can be easily transferred to other places as well. So this is related to model interpretation, and I wrote a piece in Annals of Internal Medicine about this. And so there are typically two types of model interpretability. So one is intrinsic interpretability, where like the decision trees or logistic regression, or you like inject attention weights into deep learning models, where the model interpretation is really inherited in the model building process itself. The other is post hoc interpretability. So we first learn a high performance black box model, and then we want to distill the dark knowledge out from this complex model by using this the input and output of this complex model as teachers, and to teach a student a model which is really transparent, let's say a decision tree or a forest model that can approximate or mimic the behavior of the teacher model well. So all these are important hot research topics in machine learning as well, but there are still a lot of questions and problems are yet to be studied, like attention mechanism, which is an important intrinsic interpretability approach, have achieved a lot of success. But recently, people found that a lot of times attention is not supposed to do the job it's supposed to do, but rather it serves like a shortcut or additional features that can boost your prediction performance, which is not surprising in an end-to-end learning pipeline. And we wrote a paper analyzing that, and we call this a combinatorial shortcut, and we propose some techniques by combining causal inference and deep learning to make the attention more unbiased and do the job it's supposed to do, which is interpret which feature is more important rather than serve as additional predictive features. And there are also like a post-hoc interpretation. Like in this paper, we train a black box gradient boosting tree model, and we use something called SHAP to distill the knowledge out by interpreting which feature is more important in the prediction process. But one thing that people have been studied too much is whether those interpretations are stable or no. So people talk a lot about if model is stable, but what if the interpretation, your interpretation can easily change by data perturbation, then we cannot reliably use such interpretation as knowledge in the medical applications. And also model security. So we all know the adversarial attack problem, so I wouldn't introduce this too much. But in medicine scenario, this science paper have created this example. So if we know how the model works, we can actually modify the records, let's say in the insurance claim approval process, to let the model approve the records, which cause some potential medical fraud. And we also show that not just the image for EHRs is also very easily to do such adversarial attack by just slightly perturb the lab test values. So it is possible to do that with clinical data as well. So it is important to be aware of this. This is also one problem of the small data big model scenario, because your model is too complex to fit into the small training sample. So which makes the model, especially at the decision boundary, to be super sensitive. So that causes like a small perturbation of the data can easily jump across the decision boundary. So that makes a successful adversarial attack. And the last one for the small data scenario is model bias. So this is another science article talking about using a computational model to determine if a patient or a person is eligible to a specific healthcare management program. But what the authors show is that in this algorithm, for the black patient to be eligible comparing to the white patient, it needs to be much sicker in terms of the accumulated chronic conditions. So this basically warned us. So when we develop the algorithm, we have to consider or be aware of the potential bias of the data as well as the model, and to basically leverage appropriate features, or like in this paper, adjust the model decision in a post-hoc way, such that it can produce more fair decisions. So with all that, I would like to thank all my collaborators as well as the members in my lab. And so thank you, everyone. And if you have any questions, please feel free to email me. That's it.
Thanks, Professor Wang, for discussing the applications of learning with small data in healthcare. Here, I'd like to discuss more about the applications in smart city. The small data challenge is is a critical challenge in the smart city. So in this part, we maybe have several scenarios which may facing the small data issues. So the first one could be like if we want to deploy a new system to maybe new region or like a new city, so we could not collect enough data to train a very good deep learning model. Even maybe especially on maybe several on the first several weeks or on the first several months. So to collect this enough data set, the other scenario could be like we maybe due to some policy issues, also privacy concerns, so we cannot collect enough data from the internet. So for example, if we want to analyze the Boston traffic, so we want to collect some text data in Boston, but it's a little difficult to capture to collect these data. And there are several applications about the learning with small data on smart city, like spatial temporal prediction, like traffic signal control, human movement, like smart spatial temporal missing value imputation, or the last one is environment-related applications. In this first one, I would like to focus on the traffic demand prediction, as to also see the Boston traffic, so we may not capture enough data about that. However, we could collect some data from Washington DC, like New York City, total maybe from 7 months to 6 months data and 1 year data. So after we collect this data set, and we want to transfer this knowledge to the Boston, maybe Boston has just 1 day data. So to achieve this goal, we may apply some learning with small data methods like meta learning to achieve this goal. Before we start discussing the technical details, we maybe first formulate this problem. So this problem could be a given historical traffic demand values. We want to predict the traffic demand at the next time step. For example, here we show the map in Manhattan, and in this Manhattan map, we will split the whole Manhattan map into different grids, and in different grids, so the deep color could be a high traffic demand. And we will calculate the traffic demand by using the traffic demand request within a specific time interval, maybe half an hour. And then at 9 a.m. we have 1 map, and then 10 a.m. we have another map, and we want to predict the next time step. Thus, to predict this one, we will involve some base prediction models to achieve our goal. So it could be a deep spatial temporal prediction model. So here we use convolutional layers to capture spatial information and use LSTM to capture temporal dynamics. More specifically, so for each time step, we would have some image which captures for each pixel could be the demand values and the high values, maybe the deep color. And after we're using this a pixel image, a demand image, and we will feed it into the convolution layers, and it can be and the convolution layers can extract some spatial features, and then it will be feed into the LSTM and to capture the temporal correlations. And finally, we will get the spatial temporal representations, and then can feed into the regressor to make the prediction. And here, if we have these base models, we can apply maybe a lot of meta-learning algorithms, such as we discussed before, the memo, the memo, or the different variants of gradient methods, and to help us to predict the spatial temporal values for a new city. However, there are still some we could also regard as application-specific knowledge. Here we would like to see it maybe one type of it is about region functionality. So region functionality we could see in this way. We just illustrate some regions. We just illustrate the demand value patterns across the New York City. We select one region across the New York City and one region across Harvard University. And we can see the temporal patterns from both regions are very close. So like all the temporal patterns may be higher at night. So one has one peak at night for each day. And it indicates that people transit to work. And we can regard this region functionality are globally shared across different cities, because this just represents like the functionality of each region. So maybe this region is a residential area, or like people, the traffic demand is higher in the morning, but in the working areas maybe higher at night. So like here is the New York City, New York University, and Harvard University. Thus, we want to build the correlations between the regions from New York University and to Boston. To be more specific, we will encode this region functionality to a pattern memory. This pattern memory encrypts the temporal patterns into a transferable spatial temporal memory. Here we can see the first one, the patterns are almost zero, and second one, they have 2 peaks, and the third one has 1 peak at night. And these different patterns would be encoded into the parametric spatial temporal memory, and different rows in each memories would represent different patterns. And then we will incorporate this spatial temporal memory into the base model framework. So after we get the spatial temporal representation of base model, we will use it to query the spatial temporal memory and to find which pattern is most similar to the base model pattern. And based on this, we will apply an attention mechanism on each, and then we will summarize this queried values to a new vector C, and the vector C could be regarded as the pattern vectors. And we use these pattern vectors with the spatial temporal vector H, and then feed into the regressor. And note that, so since the spatial temporal memory is not like a global share, it could be because it encodes patterns, so it could be regarded as a global shared memory. So here we just use this spatial temporal memory as learned in the training process, but we fix it in the testing process. Let's see this procedure of in the meta-learning part. So we will integrate all the information into meta-learning. And in this meta-learning framework, we will have several source cities, and then we will sample some tasks from these source cities. And then we would like to split it to the training and the testing set. After the training set, we will do train the base model, just do the task adaptation to the base model. And then we will also use the representations to feed into the spatial temporal memory, which could be fixed during the testing process. And then in the training process, in the meta training process, we will use the loss function to go back to optimize the parameters of the model initialization and the parameters of spatial temporal memory. Okay, so let's focus on the inference process. In the inference process, so we will sample some tasks from target cities and split it to the target training and the testing. So, and then with the base models would also be fine-tuned by using the training set, but we did not do anything on the spatial temporal memory because we cannot collect enough data from the target cities. So maybe based on some bias, and then we will also evaluate on the testing set. So this is the basic frameworks about integrated into the transportable spatial temporal memory into the meta-learning framework. In this part, we will show some performance. Here we show one data set, and you can read more on this paper. And this data set consists of the taxi trip records. So it consists of source cities like New York City, Porto, and Washington DC, and also the target city is Chicago. So we assume we have 1 day, 3 days, 7 days data to train the model. So in this part, we can see the prediction performance, especially on Chicago. we can see our models can achieve the best performance of that. And besides this, we have like a more, we also do some analysis on like the assigned patterns. So here we can see like the pattern 1 and the pattern set, region 1 and the region 6 activate pattern 1. So both are like a very so like remote areas which do not have some many traffic demand requests. And the region 3 and the region 5 activate the P3, so the pattern 3. So we can see region 3 and region 5. So both regions have 1 peak at night, and the region 2 activate like the region the P2 and the region 4 activate P4. So both of them like is also some show some interpretable results. So here is the first application about the spatial temporal prediction, especially on the traffic demand prediction. In the second applications, we will discuss like about the intelligent traffic signal controls. So like in the traditional traffic transportation, so we will like to using to optimize the traffic control policy by just optimizing with some assumptions, maybe like minimize the traffic time with subject to some traffic models, and then the traffic signal is could be a function of emissions. Emissions could be like the current like the status of different traffic status, like maybe how many vehicles waiting in the road, waiting on the signals, and also but with after that we can collect a lot of data, and then we want to use reinforcement learning to optimize with data, and here we also have one agent, and it could be just give some actions, and then the environment will get the feedback to the to the agent, and then after optimization, the policy and the agent could given a very accurate actions, so to control the traffic signal and can to reduce the overall travel time. The key point of by applying the reinforcement learning approach for the intelligent traffic signal control is about trial and error search. So if we can see, we will design some rewards and to capture it. So maybe if we still be red, so the reward was down. But if it's better, it's the reward was up. So by calculating maybe some average travel time about that. However, there are still, this is some backgrounds about the reinforcement learning to intelligent traffic light control. However, there are several challenges. So if we want to deploy a new traffic light, intelligent traffic light, or cameras into a new city, and we want to apply it or a new intersections. So we want to reduce the cost because it's a trial and error search is very costly, especially in real world scenarios. For example, here is intelligent traffic light control. So how to learn faster in a new environment? So here we want to apply meta learning on it by just learn from a lot of intersections. Maybe here is intersection A, B, C, and then transfer this learned experience to help the prediction, help the policy learning in the new intersection. To be more specific, we will first discuss about the base learners in the meta learning. So in the base learners, here is we want to summarize some, propose some methods in the traffic signal control. So here we can also see their traffic signal control scenarios is very complex. So maybe there are different types of intersection structure, like right lane, through lane, and left lane. And so maybe different phrase has a lot of had two movements, and then if we do some rotations and flapping, so things maybe not change too much, but maybe we have a lot of very similar scenarios. So we have very complex settings, but we can summarize it by do some categorize of these settings, and maybe with some rotations and flappings, maybe they are very similar. Here we propose one model is about structure agnostic models, and which summarize different phrases into the model, and different phrases could be shared some parameters, and later we will summarize it to do the prediction. However, after using the base model, we want to apply the meta learning on it and to control the traffic signals, maybe in a new setting or in a new scenario. So in this part, we will discuss about learning from multiple traffic signals, and which has two adaptation levels. The first is the individual level adaptation, and the second one is global level adaptation. And here we have define a meta learner, which is deployed by theta t to theta t plus 1, which is achieves a global level adaptation. And we also have the learners, so which were adapted by each time steps. As a memory, we will also sample some data set from the the meta training part. So in the meta training, we can see we have the t and t plus t theta minus 1, and which we have one types of time steps, and we use these time steps and to apply it on the meta learning part. And for each time step, note that for each time step, we will do the one individual level adaptation. So for each time step, and use different data sets to update the policy. And finally, we will summarize all these things and do the global level adaptation. Here are some results about that. We have one data set which controls 26 traffic signal scenarios from 3 cities. One is Hangzhou, Jinan, and Los Angeles. So we will use the average travel time as a metric to evaluate the performance. So for a single cities, we evaluated in the homogeneous and heterogeneous settings. So both settings, maybe homogeneous, we will use the similar phrase, yes, and transfer to our new phrases. And for the heterogeneous settings, we will consider more complex settings about that. And we have seen the meta achieve better performance than other baseline models. Finally, in a more complex scenario is about multiple city transfer. So in the multiple city transfers, we also apply for both homogeneous and heterogeneous scenarios by regarding maybe if we want to control the traffic signals in Jinan, and we will use the Hangzhou and the LA as the source cities and to transfer it to a new city. So we would find if it can significantly improve the performance. So this is one type of the learning with small data on traffic signal control by transferring the knowledge from multiple cities and multiple intersections to control the new city or new intersection. And the part small data learning is we want to use it to help us to design to do some learning from demos. So in here we have we can collect a lot of trajectories from demonstrations. And then because we have maybe simulators, and we can use these simulators to capture a lot of demonstrations. And then we will fit into using the actuocratics methods to train these models and to find the policies. So later we will find a policy, and this policy is very close to the expert. Because here is that we do not have enough data, but we can use the traffic signals, demonstrations to help us to collect more data. And this data can help us to do the to train the models, especially policies. And later we can put it in a real world scenario for the further explorations. Okay, so this is the second applications in the smart city part. So how to leverage using the learning with small data methods to help us tackle the some challenges in the intelligent traffic signal control. The third application is about the mobility knowledge transfer across cities. Here we can see assuming we want to have a lot of data in Beijing, so we have the restaurant, the map data, and also have some data like in Hefei. But we want to like transfer these multiple source data or like the trajectories of the source cities to help the learning human mobility in a new city, like for example, quite a new city like Xiong'an. And we also want to like collect some multiple source data of Xiong'an, like also like the road and like the train, like the restaurant, but we do not have enough like human mobility data. So we focus on these problems at 3 stages. The first one is intention emerging, and the second one is destination selection, and the third one is path selection. So for the first part, we want to like do the multiple mobility intention transfer. So intention could be like, for example, here is that if we have the home, we want to go to the supermarket, but if we are in a railway, so we maybe want to go to working. So and the source city 2 maybe here if we have like in the home, and we will want to go to the store, and in the home we also will go to the working area. But in the bus, we are preferred to go to the working areas. So we have different types of trajectories. We want to first do like the spatial context feature extraction, so to extract some like features from source cities, and then we do some domain generalizations about that. So to like summarize these similar issues. So from home to another locations. So here is like 1 and 3, and also like 5, 4, 2 is also the destination is similar. So they are both to the working areas. So 2, 4, 5, and it will be also to do some to be modeled in a mobility intention space. So and using some generative model. And later, after that, we can model the intentions. We want to like do the origin destination generation. So based on the class structures and based on the mobility intention space, well, we want to like generate some mobility intentions about that, and to find the most similar origin destinations. Finally, after we get that, we want to like do the path generation. So we first have some candidate path selection, and then use the candidate path selection to find the shortest path with some overlap constraint. And later we will do like the path probability prediction, and because we will extract some path features about that, and to get like the score functions of that. Finally, we do some softmax functions and to select which one would be most similar, and to generate some origin and destinations, so to help us. So this is all these 3 applications I want to discuss in the smart city. Here we discuss like first discuss the traffic signal control, discuss traffic prediction, traffic signal control, and the human mobility modeling. So in conclusion, so in this tutorial we discuss 2 ways to tackle the small data challenge. First is for transfer knowledge from auxiliary tasks, and transfer knowledge from domain experts. And also we want to like discuss in the transfer knowledge from auxiliary tasks, we discuss the transfer learning, multitasking learning, and meta learning. In the meta learning, we discuss gradient-based meta learning and metric-based meta learning. Also, 2 challenges are discussed in the meta learning. One is task heterogeneity, and the second one is the meta overfitting. In the last, we discussed some online meta learning things, which could be like feature directions of one meta learning ways to tackle the non-stationary distribution. And then we like discuss some ways about transferring the knowledge from domain experts. So one is using the domain knowledge to guide the loss function, and one is using domain knowledge to guide the model design. And finally, we discuss some applications about healthcare and smart cities. So this is the conclusions of this tutorial. So thanks. Any questions?